session of today. Our first talk is going to be invited talk by Eran Yahav. Eran is professor at Technion, and he's also co-founder of code2vec, a startup that does interesting things in this area. Earned his PhD at Tel Aviv University, and he was leader of a research group at IBM Research. And he is now at Technion. He's recipient of ERC grant, which is a very prestigious and very good funding from European Union. And he's well known for his work in analysis of concurrent programs and other kind of program analysis. So now he has discovered the charm of the topic of this workshop as well. So he's going to tell us about code2vec.
All right, thank you, Victor. So this charm has actually been discovered like 6 or 8 years ago, the charm of analysis at large scale and learning from programs. And we've been doing a lot of work in this space. So I'm giving the talk, but really it's the work of many people who appear here. There's a bunch of papers that you can look at. A lot of what we're doing is open source, so you can try that. All the demos that I will show, you can try them for yourself. And some of it has been commercialized by code2vec. And so what we're really trying to do in this research is kind of like the vision of synthesis. It's similar to the slide that Swart had earlier, which is we have the programmer, we have like some models that we learned from all the code in the world, and we'd like to somehow augment the programmer intelligence by having her communicate with the models. So she communicates her intent, the models do some magic and give you back the result. And if you do like this kind of conceptual model, you can predict code, like automate all the mundane tasks that the programmer has to do, keep the developers on the main path, and give them code that is likely by construction. So there's no really notion of correctness per se, but likelihood. Or you can check code and check that it conforms to what we have learned from all the code that is out there. And what I'd like to do today is not talk too much about the interaction model, although it's very, very important, and we can talk about that offline. I want to talk about models. I want to talk about a particular model, which is called code2vec, which is a model that we developed recently. It's a neural network for predicting program elements from context, and we released it a few months back, and it got like kind of some traction. People have been really interested in it because it's very, very simple. And the goal of this talk is to convince all of you that this is something that is simple and useful and that you should use it. And I'll try to give you all the kind of gory details that will allow you to do this exact thing yourself. And so this is actually a general model, but the way I'm going to present it in this talk is for the specific task of predicting method names, and this is a task that has been suggested by Miltosh back in 2015. And so I'll just demonstrate everything on this task, but as I show things, you should keep in mind that this is actually a general model. And I'd like to start by just giving you some demo of what this stuff does. And I'll move around a bit. I hope that some of you can see some of the code on the slides. Yeah, all right, good. And so at this point, I'd like to ask the volunteers in the audience, what does this code do? Like, can you tell what is it that this code does? Sorting, bubble sort, excellent questions. So we can, instead of asking the audience, ask the model, and the model says, yes, you know, this is sort, very high probability, bubble sort with some lower probability, and you know, it deteriorates from there. So let's do another one. Again, audience participation encouraged. Contains. All right, let's do that. All right, thank you. This is contains, very high probability, or matches, or can handle. And ignore for this second, ignore what is happening at this part of the slide. And let's just start changing this thing. All right. So instead of returning Boolean, let's return object. Instead of returning true, let's return target. Instead of returning false, let's return null when it's not found. All right. Try again. Are you hitting the site yourself? Because that's like not going to help us. All right. But okay. But you could, by the way. I think I increased the capacity there, so you can try it yourself. All right. So now that we changed it to target, you see that we get the prediction get target. And so maybe this kind of hinged on the name being target here. So we can say, OK, let's do it foo instead. equals foo, return foo. Wait a bit. And you see it became get. So something is going on here. We're getting some predictions that are sensible, right? I'm changing code. And in a sense, this is kind of what I'll show you about this model is it is the happy marriage of structure of the program and kind of natural language information like names of identifier things in the program. It kind of combines them nicely, and this is what is happening in here in a sense. So any questions so far? The floor is open for questions at any point. No, nothing. All right, you want me to try and destroy it? Because we could, yeah.
So is the main target and understanding, sort of have a summary that can be...
So at this point we're just trying to predict some labels of this code, or you can think about it as the method name, just trying to create some description of what is going on, like what Miltosh called at some point extreme summarization of this piece of code, right?
I'm just curious, so the name is coming from a finite vocabulary?
Yeah, at this point, at this demo, the name is coming from a finite vocabulary. We have like an improvement of that in which there is decoding going on and the names are generated. But for this demo, the names are fixed vocabulary. Any other questions? Yeah.
And it has to be a function, or can it just be a function?
It can be any piece of code. It's not, there is no real restriction. Yeah, the meaning of the diagram will be clear as we go on. Yeah.
So could I obtain get target even if the word target does not appear inside?
Maybe, I don't know. So we can try, but I don't know what will happen.
But indeed, get did not appear. Right?
Yeah, get did not appear. Yeah. So I think there are more. We can do like more obscure examples if you want, like this. It's factorial, okay? So this is factorial. I think we can agree that it's factorial or fact or these things, right? And the word did not appear anywhere there. Actually, in the sort also, there was no mention of sorting. Yeah, what happens if I break it? We can break it. So we'll break it later. We'll break it in a bit to a million pieces. Sorry?
If you put plus instead of times.
Oh, Victor. Well, you're making my laugh hard. Yeah. All right. So it's an excellent question because it has a good answer. It is no longer factorial. It's actually n. It's actually nothing. All right. It's you kind of dropped off the edge of the model in some sense because it has no good name for this. Right? It's like it's got some nonsense names here because there's nobody writes this kind of code in a sense. They don't observe it in the wild. All right. So any more questions about this before we go to the details? All right. Go to the details. So how does this thing work, actually? So what we're really doing, as Rishab was kind of hinting, we're trying to learn distribution of the tags conditioned on the code. And at this work, the tags, the labels are a predetermined set from the training set. So it's a predetermined vocabulary for the training set. And somebody gives me a piece of code. I'm trying to predict the likely label. And the question is how to represent this C, how to represent this piece of code such that we can condition on them. And in this work, we're going to use syntactic paths. And before I go to the details, I want to just say in this forum, a very important message. This is a PSA. A program is not just text. All right? So we've seen some work, and we've done some work ourselves that treats program as a token stream and tries to learn over that. That is very limited because when you look at a program, some regularity is already known from the language definition. So if you just try to treat it as plain text, what you're really doing is you're relearning, in a sense, the language syntax and some rules of the language semantics. And it's not all bad because there are some trade-offs here. Like if you're relearning, you need much more training data and longer training, and sometimes it is infeasible. But in some sense, you can be language agnostic, right? Because you're relearning everything from scratch. And so there are some trade-offs here. I think of it as this kind of diagram. So this shows like how semantic is the semantic depth of your representation, and this is kind of the learning effort that is involved. Right? And on the left-hand side is like program text. And if you're just learning over program text, you basically have to make like tremendous effort because you're implicitly relearning the program syntax and everything else. If you go all the way to the right here and like doing very deep program analysis, it's great. You have reduced your learning effort, but you became maybe very language specific or task specific because you've done this analysis, you tied it down very rigidly. And so what we're mostly interested in is like working in this area, around this area here, like doing just enough program analysis to make the learning effort decrease significantly, but not too much as to become task or language specific. All right, so this is the key slide of all the talk, of the entire talk, and I can leave now, but because you gave me so much time, I'll try to fill it with interesting things. Yeah.
I don't understand why semantic analysis needs to be problem and programming language.
It need not be, but as you make it so, you're tailoring some properties of your language, like talk about the notion of Swart head loops or whatever. So maybe my language has something else. I don't know, maybe loops are not, maybe specific APIs, maybe types, maybe.
But I think there are many questions that are semantic, like of a long-range flow of information and so on. Question about the interprocedural analysis.
But for example, if you're doing, let's say, a data flow kind of thing, you need to start to understand the notion of scopes, right? And so scoping rules may be very different between different languages. So either you relearn them or you encode them somehow. Basically, it's a limit argument, right? In the limit, you're becoming more, as you become more semantics, talk about the traces, you need to understand the language. In the limit to the left, you just understand text, right?
But
it need not be, right? As you're saying, the sweet spot is finding these representations that are not language or task specific, but do capture some semantic information.
But is the problem with going to the right that you want to support many different languages?
And many different tasks.
It's the task?
Yeah, languages and tasks, and you can do things like Martin is doing, which is basically per task or per language, learn automatically the representation that you need to be somewhere on this curve, right? But if you want to do there are some way that you can go with some general representations like the one I will show now, right? So that's kind of the gist. And because I think Michael talked about specifically Word2vec, I wanted to make the point that if you look at Word2vec, you can describe the notion of what you're predicting, like a particular word, based on the neighboring, you can describe the context, like the neighboring tokens around it, like you did and like Word2vec over text does. Some people have done like surrounding AST nodes or something like that, some other notion of locality which is in the AST. And what we're doing intuitively is we're doing this thing using AST paths, which I'll explain in a second, which transmit context information over a long range over the AST. It's not just a small neighborhood around it. But maybe this is kind of premature. I wanted to just give you the intuition of that to the ones who know the notion of context in Word2vec. And I'll just explain what AST paths are, and we can work from there. Are there any questions? No. Yeah.
I just get a note, like, I think in NLP they have this also the semantic lattice is common, like when you do translation, do you go from like purely syntax or do you like twist it a little bit? Not in some, yeah, in summarization, abstracted summarization, concrete summarization.
Yeah, so
Maybe this is also like good for
yeah, could be. All right, so let's look at these AST paths. All right, so technically this is what I want you to understand here. We're going to represent, the question is how do you represent code elements basically? And the way we're going to do that is we're going to look at a code element like this done here. And we're going to represent it basically as the set of paths that in the AST that this done participates in. So let's look at one path, for example, within these two instances of done and done. And so what is an AST path? It's just a visit or a walk on the AST, starting from this done here to this done. So let's look at it, how it looks. So every step we take, we write like the node that we visit in the AST and an arrow that tells us what is the direction. So we say we go from the symbol ref, we go up to the unary prefix negation, up to the while, down into the if, down into the assign, down into the symbol ref, and then self, which is done itself. All right, so that's just a path which is a visit of or a path in the AST, but I want you to look at it for a second. It's a very simple syntactic thing, but if you look at this path and try to think what it captures, it is actually quite interesting. So what this path captures, really, intuitively at least, is the notion of doneness, right? Because what does it capture? It captures the fact that me, done, I appear somewhere where I am the stopping condition of a loop under negation. And then inside the loop, there's an if in which I'm assigned true, which basically stops the loop, right? So if you think about this intuitively at least, this path is just a syntactic path in the AST, but it somehow captures the semantic notion of being done, of the doneness. And if we look later at this kind of gives rise to embeddings that are very rich, and I will show that a bit later. Yeah.
It's not clear to me how this generalizes when you have 3 occurrences of something.
Yeah, so you can basically, it generalizes, and the thing is that right now we're doing pairwise things, but you can obviously do it like we do in binary features, but you can do it like k-array or whatever. And the way we represent the code is not just using this single path. You represent it as the set of all paths in which done appear. I'm just showing one here for intuition, but actually the way we represent this code is also the path from the some condition to done and from the true to done and all these things together, right? So there's a huge number of paths. Actually, you should be worried not about generalization, but about the number of paths that this gives rise to. And I'll talk about that a bit later. Other questions here? Richard?
Yeah, so essentially, AST converted into n squared paths where n has the leaves.
Yeah, exactly. Yeah. So it's a quadratic number of paths in the AST. Other questions?
So why is this better than AST?
So I'll explain. All right, so the question is, what do you do with it, right? As is, it is not better or worse than anything. It's just a representation. The question is, what do you do with it? Yeah.
So how are these paths defined again? It's always starting and ending at the same identifier?
No, it's between leaves. So it's like between leaves, yeah. So these are paths in this particular case. There are many ways in which you can use these paths, but in what I'm showing for predicting method names, right, or for predicting this kind of thing, it's going to be the quadratic number of paths between leaves in the AST, right? Yes?
So what if you don't have paired leaves?
No, they do not have to be paired. So I also have the path from some condition to done is also there in my bag of paths. I'm not just matching done to done. All right, this done to done is maybe confusing because I was just trying to give you the intuition. Yeah?
Is it important that the paths start at a leaf and end at a leaf?
No, we also experimented with partial paths, paths that break in the middle out paths, everything. And it's just the idea is that you need to somehow linearize this AST to things that are easier to work with, right? A bag of linear things, like features. And this is one way to do that, right? And I think there is something interesting about paths from leaves to leaves, from a leaf to a leaf, because they do capture often, especially when it's the same identifier, they do capture some interesting semantic property of what is going on, like how this thing is really being used, right? That's our experience at least. Any other questions? Complaints? No, all right.
So here you're following these edges in the parse tree, but could you also imagine following other kinds of edges?
Yeah, you can do this on dependence graphs. You can do this on all sort of things, and we did that. It's on dependence graph again. The problem is that you have to build them, and building a dependence graph is expensive, etc. This is all large scale, right? You run it on tons of code. All right.
But ultimately you get a set, right?
Yeah, it's a set of you can call them binary features between AST nodes here. Yeah.
It can be a set of anything essentially.
Yeah. I think that the next slide will maybe make it clear that how we use it is actually the interesting part. Okay, this is one way to extract these paths. And so what we're going to do with them right now is to predict method names or method labels. And so the way this is going to work is that on the left-hand side, I have these discrete objects, these paths, say from done, I have the path to done or whatever, but I have a bag of them that I extracted from the method. This is often huge. On the right-hand side, I want to predict a label for this method. And in the middle, there's going to be some neural architecture, which is very, very simple. And that is the beauty. The beauty of the work is in its simplicity. Okay, we're not trying to be super clever. We're trying to do something that works well. And this is roughly the architecture at a high level. If you're not used to reading kind of thing, I'm going to walk you through. So basically, the first step that you have to do in order to work with neural networks and these paths is to embed them into continuous space. So we have some embeddings here, and we take like the source, the path, and the target, and we embed each one to a vector of dimension d, right? Then we basically concatenate them to get one representation of the path, have a fully connected layer to shrink this somehow into, again, a vector of dimension d, and somehow learn how to mix the three components together, if you want this intuitively. And then we get this code vector, and the important thing of this entire network is actually the attention, right? What makes this whole thing work and what makes it interesting is the use of attention here, because this tells us how to take into account different importance of different paths that started here, right? So the question is, what is the importance of each path that we started with? And this attention gives us actually double benefit. One benefit is that it allows us to be more precise, like it improves the prediction, but the second is some sort of interpretability. So we can understand why are certain decisions being made, right? This is the important thing for me, at least, in this network. All right, so I hope the architecture, at least at the hand-waving level, is kind of clear. It is very simple. The important thing is the attention, right? And let's see what it is able to do. Yeah.
So different programs are going to have different number of elements in the set.
Yeah.
So how does that?
It's a pain. You have to deal with all sorts of these things.
So the code vectors are trained via the prediction path, unlike
Yeah. So the training is basically taking, as usual, taking many programs and like throwing them here and like with the label. And basically you learn both the embedding. So the important thing here is that you learn the embedding and the attention simultaneously, right? You learn the embeddings and the attention simultaneously. It's again some kind of useful thing. Yeah.
So what is the prediction is?
Just a label from our label training set. Like, so we have fixed vocabulary of labels for this work. Yeah.
Is one hot encoding or?
No, it's not. It also has embedding, which we learn.
Okay.
Yeah.
So I didn't quite get, how do you embed the path? Because it's variable length, it's a gigantic vocabulary, so what?
You do stuff.
Stuff.
Yeah. You do stuff. There are some things there. I mean, it's not, I don't think it's for here, but.
Give like some direction for the stuff.
So the stuff.
Move in a certain direction.
Yeah, sure. Stuff can range from padding, which is the basic stuff. So you assume some maximal length and you pad the hell out of it. And can range all the way to doing RNN encoding of the path itself to something that is much more compact. All right? But there are many ways to solve this. Again, these are like, I call them technicalities of the encoding. It's not the interesting bit here, I think. Although it's, as you imply, it's very hard, actually, technically. Any other questions? All right, so what you get from it, really, I can show this actually in real life. So let's go back to factorial before we destroyed it. Put it back and do the prediction with factorial. And what you see on the side, on the right-hand side, now we can actually understand maybe what is going on. What is important here is not the color of the path, but the width of it, and the width is proportional to the attention given to this path. So what this means here is that the reason, or basically some hand-waving question, the reason for calling this factorial or fact is this fact path here that says, hey, you're taking the identifier n, and you're multiplying it with a recursive method called code2f, passing n minus 1. Right, so this is what makes us call this, or this is why the system thinks, this is the justification for calling it factorial. Yeah?
Have you tried seeing the nearest neighbor, let's say, so?
For factorial, yeah, factorial.
So, because there was another functions in your training set that was called factorial.
Sure. So this is maybe too contrived of an example, in a sense. I agree with that. But we can
Visualize what happens if you commute the factors here. So if n, if it's f of m plus.
Sorry?
N.
You want this is.
Swap the n times 2 times n. Just curious what happens.
I have no idea. You and me
I'm
both.
curious to see how the weights on the.
You and me both. I have no idea what will happen.
But that's
Yeah, it did not work, and the weights are like something different happened. Now we think something that the parameter is n is the important stuff.
But this is surprising because a human still recognizes that this is factorial.
Yeah, but this is not a human, right? I think we can agree on that. So there are many.
Get this, because the set of paths should stay invariant to this change, right? Because the
Sure, maybe the set of path, it's not exactly invariant, I guess, right? You did something that is.
It's leaf to leaf. That's still a leaf, right?
No, but the path is different, right? And so.
Learning methods for this should be very similar.
So the short answer is I have no idea, guys. This is what the model produced here. We can investigate it further. I don't
What
know.
I'm trying to understand is that the set of paths, is it not the same in the two cases? Should be, right? Because it's still a leaf. I mean,
But it's different. No, it's different, left or right, yeah.
oh, I see. Okay.
Yeah. It's not the same. It's not the same. The attention is not the same. I don't know. We can go to simpler examples or something that is not factorial, basically, where the space is less sparse. Yeah, you can try that. So this is why we thought.
Change the lm equals target, but target equals lm.
Again, what do you want?
Yeah.
We can listen. It's not. It's very easy to make up adversarial examples in which this will do stupid things, and we have done that, and I can show you more and more of those. But let me first, before we go adversarial, let me explain when it does work. All right? This is not supposed to be human. So I want to explain, for example, why the model thinks this is contains. And if you look at the path here, you will see that you're iterating something that is called elements, basically. And there's some if statement, and then you return true under some condition. And the other reason is that there's some parameter called target, in which case there's an if and you return false. All right, so one maybe message that I'm trying to make here is that there is no single path with which you can explain what is going on. This is the meaning of the attention. It kind of weighs together multiple things to reach this conclusion that this is the label that should be. And now let's change it again. Now we can start, whatever, return target and return no. And we can run this again, and now it says the name is getTarget, and I guess there's less of an attention on this path and more attention on this target. And now we can do, whoever wanted to break this, we can break it. All right, so let's start breaking it. For example, you can do like object deleted equals lm, and it's not deleted at all, right? And then just return deleted. And I don't know what will happen. I can kind of guess, right? That it's like is deleted, right? And so because the names do play a role and something is going on here, and the space of labels in this work, and the space of labels in this work is still kind of sparse. So you often fall into the same kind of naming. Any questions about this? You want to break it some more? No?
Can you reverse the Boolean expression there?
Reverse it will still be contains if you want, like not.
And then reverse the results.
So I think you're thinking like Cav, and you should stop thinking like Cav. This is this is like not doing anything that is deeply semantic. It is taking the paths in the AST, it makes some embedding of them, some mishmash of them using attention, and then does the prediction. And when the label space is so sparse, then often manipulation of the expressions still fall into the same kind of label. Does that make sense? Yeah. So let's go back. I think that the nice thing is, again, that even if you take examples that are seemingly very similar, like this one doing contains and this one doing get, you can see that the model separates them, and the model can give you some attention as a hint, like this attention thing, the weights, as some hint to why the results look as they are. And I think I already showed you this on the system, on the demo, and I don't need to show you this on the slide as well. All right, so let's look at some more things. Back to attention embedding in a browser. So I think this is actually for Michael mostly, that the embeddings that this learn are very, very rich and interesting. Like I can ask what is the most similar to count, and I'll get like get count, size, index, sum, max, stuff like that. I can start to ask about combinations, like if you do equals and 2 lower, what do you get? Audience participation encouraged. Equals ignore case, right? Because this is what you get when you do equals and 2 lower. And you can do analogies like receive is to download, as send is to upload, and you can do whatever. You can do like delete or something, update or save. And so these are very, what you get are very rich embeddings, because these paths, what they give you is like very kind of, I don't want to call it semantic, but the relationship between the name and the structural role that it plays in the program is very tight. So I view this actually for you guys who are talking about bimodal modeling. This is really the kind of the best way that we have seen so far to connect this kind of space of names or space of semantic entities known to the user with structure of the program. Yeah. So these embeddings are a side effect of this network. Right? So these embeddings are a side effect of this network. Yeah, sure. This is for the task of predicting the label, right? Yeah.
So sorry, this is my lack of word-to-vec understanding probably, but analogy question, how is it phrased in terms of the vectors?
Minus, basically, like this plus this minus this, yeah. So just like the combination is just addition, you do this plus this minus this is what? Yeah. Right, so that's like the transformation of analogy. All right. So as I said, you can use this network, I'll skip this. You can use this network to do all sorts of predictions, like Martin did with the CRFs. You can basically predict method names, variable names. You can predict method names like we saw. You predict actual full types in Java, like the fully qualified name, or you can do this for JavaScript to predict types, and you don't need like gated neural networks. You can use these things much simpler. And how much time do I have? Not that much. All right, I'll do what I can. So I want to talk a little bit about, so this is, I'm switching gears here to something that is completely different, called prediction. I just want to make the same point again. You can do some, yeah, Martin.
I just had a question, like, so this model is like interesting, it does all this combination, you can use it to like solve different tasks, right?
Mm-hmm.
So, and then you're done, you solve like tasks with some prediction. But you can take the embeddings, I guess, after this and use them for another task.
Right, yeah. So I think we're going to give our embeddings to Michael, and he's going to try to use them for deep bugs, because the embeddings themselves are rich and interesting. Yeah. So but this is a side effect of doing this training. Yeah. So thanks.
So for this task of variable names and types, does the model still need to encode the full thing, or does it do something localization?
So it does paths that are into the tag that you're into the location that the node that you're trying to predict. You don't need to do like the quadratic number anymore. You're just doing like focusing on the element you're predicting. Yeah.
And I guess you can do subsequences on the path to like do the loop around.
Yeah, you can. The paper has like subsequences and various abstraction of the path. This also goes to your question of like how do you encode this, because you don't always have to take the whole path. Sometimes you take just the edges. Sometimes you take like some node in the middle. Sometimes it's enough. And so there are different abstractions of paths that you can try, and some of them are more scalable and quite precise. So to reduce kind of the training effort significantly. All right, just to until the time runs out, I want to talk a little bit about recurrent neural networks. And my point here is, again, program is not just text. If you are trying to do like prediction of the next token or something in your program, trying to predict some tokens based on the prefix that you've seen, if you train it at the character level, there's a certain kind of behavior that it will get. If you're training at the token level, there are certain things that you cannot do. And if you're training on something that is more semantics, you may get better results, right? So the more kind of semantic that you get, the deeper that you do the analysis on the program, the better predictions you will be able to get out of this model. All right? So again, a program is not just text. Right? There's a limit, there's a hard limit to what you can do with text-only modeling. And so in the kind of like last part of the talk, I want to talk a little bit about something completely different, which is what does a recurrent neural network actually learn, right? And so we have some experience with extracting models from RNNs. So this was motivated by our work on trying to predict like next token in research about programs. But then we saw that sometimes the network is really surprising, and the results that you get are really strange. And so we started to ask ourselves, what is it that the network actually learns? And to do that, I'm going to step back from programs. I'm going to talk a bit like just a classifier of email addresses, because it's a much simpler example to deal with, no programs. So if you are completely lost up to this point, there's a chance that you can redeem yourself and understand what is going on here. All right, so join us. And basically, the idea is the following. We're going to take positive and negative examples of email addresses. We're going to train some recurrent neural network. So let's say we take 40,000 example or 40 million example, doesn't matter. We reach 100% accuracy, obviously on the train set, but also on some test set. And the result is the RNN, which is literally a black box. All right, so we don't know what is in there. And the question, has it really learned to recognize valid email addresses? That's what we would like it to do. And using our method, you kind of like extract adversarial example from the RNN quite quickly and show that it accepts email addresses like 25.net, 2hs.net, etc., etc. So very strange things. And this is a very, very simple exam, very simple problem, right? We're just trying to classify email address as valid or invalid. You can probably write the regular expression for doing that in 5 minutes top, right?
No, it's actually very difficult.
Very difficult.
Yes. If you actually Google for it, you will find the regular expression to check whether an email address is valid or not. It's very difficult.
I think I disagree, but
you're looking at there,
I think...
I mean, the real one.
Oh, yeah, the real one may be very difficult, but let's see. I think I wrote it somewhere because I remember that. Okay. Some version of the regular expression for identifying valid email addresses is very simple, and still the RNN does not get it. Yes.
So this, for example,
sorry?
What's this for negative examples?
We randomly generate mutations of some emails like that we know to be invalid, so we have some mutations. Yeah. All right, so we agreed. What did we learn so far? That the real regular expression for identifying email is very, very difficult. But even the simple one cannot be learned by the RNN, and you don't need 5 minutes to learn, you need 50. All right, great. But still the RNN kind of like does something wrong here. And the question is, how do you know it? And so to kind of get that, we ask the question of what happens if you train the RNN over a completely irregular source, just take a regular language that we know, take an automata, generate some sequences that you know is a regular language, everything is great. You train the RNN, get this black box. And then, like at a separate pass, yeah, this is you stop, and now you try to extract the automata and get some other automata and compare them at the end. Right? So the exercise is I train my RNN based on an automata, I stop, I go home, I come back tomorrow, I take the RNN, which is the black box, and I try to extract a DFA from it and see how the DFAs compare. Yeah.
So theoretically, it could represent DFA, right?
Yeah. So theoretically, and I'll touch on that at the end of the talk, theoretically, LSTMs are Turing complete. All right, so in general, they could represent this. Practically, the reduction that shows that they're Turing complete is not very useful, maybe. And I'll touch on that in the last 5 seconds of the talk. All right? So basically, the question is, how do you get, you have this RNN, it's a black box, how do you get an automata out of it? So one thing that you can do, and people have done that in the 90s or something, you view the RNN basically as an automata over continuous states. So you just take like, you treat the initial vector as initial state, you treat the RNN cell as a transfer function, and you can basically just try and run this. So you can take some values, let's say you have an RNN over 3-letter input, so let's say A1, A0, A1, A2, and you can just run the network and see what happens. So you say, here I start with the initial vector 0, 0, and I convert the input to whatever one hot vectors or embeddings, doesn't matter. So I have AAB, I put A in, I get some new state, 0, 1, 0, 2, right? Because I run the RNN cell, I make a step. This is the new state. And I can plot it. So here it is plotted on this two-dimensional thing. And my RNN is very, very simple. It's like I have just two vectors, two floats in the hidden state. So I can draw it on a 2D plane. And I can make steps. So I make the next step. I get like 0, 8, 0, 2. I plot that. And I make another step with B. I get some values. And I plot that. And if I keep on going, I'll reach the classifier at the end, which will say whether this word should be accepted or rejected. And now I put a color of green or red on each state, whether it has been accepting or not. And I can keep on going. And if I keep on going, ideally I will get something like this. I keep on playing, and I'll get this nice automata that describes exactly what the RNN has learned. But, as we know, life is hard. And so in reality, the values do not repeat, right? These are floating point computations. You get some things, and the values are kind of look like that. And you can basically keep on going infinitely, even when, in reality, these are closed values that intuitively should have been clustered to this. You just don't get that, right? And you don't know how to get that. All right, so the problem intuitively is that you played the RNN, or you unrolled the RNN, explored the state space, you got something like this, and the question is how to get back to automata. Does that make sense? You're dead, you don't understand what's going on. We're good, all right. You know what an RNN is, yes. All right, good, excellent. All right, so one idea that is due to Omlin and Giles, 92, is to partition the space, which are basically quantize the network. So you can just say, I partition each dimension to 3, and I'll just run the LSTM or the RNN in that. So I start running, say, OK, A, and the square is the abstract state of the automata. I make another step, and if you've played with quantization abstraction before, you know that this is going to hit trouble, right? Because you're going to have some rejecting state inside an accepting state, and then what do? You split, you do refinement, and this becomes non-practical very quickly, because you're starting to refine these dimensions. It's like, this is not two-dimensional, right? It's much higher dimensionality, and this explodes very, very quickly. You cannot do that. So what we have done, and this is a paper that appeared in ICML a few days ago, is basically use Lstar, use exact learning of regular languages with an abstract teacher. So if you remember what Lstar does, what algorithm does, it basically learns an automata from a teacher by asking two kinds of questions. One question is a membership query, asking whether a word is in the language. And once you've established some hypothesis automata, you can ask the teacher, is this the automata? Am I equivalent to what you had in mind? All right, so this is just a refresher on Lstar. Let's say I want to learn the concept of the language that starts and ends with the same letter over AB. Empty word is accepted, so I start. This is just Lstar, no RNNs. All right? I start by asking empty word AB. The teacher says, yes, I accept all of them. Then I say, here's my hypothesis about the automata. And the teacher says, no, this is not the correct automata. And here's a counterexample, BA. And now I ask a few more questions. Like, is BB in the language? Is BAB in the language? And the teacher answers. And now I have a new hypothesis. And I ask, is this hypothesized automata what you had meant, dear teacher? And the teacher says, no. And here is a counterexample. And I can keep on going until the learner gets the right automata. All right? So that's kind of the intuition of what Lstar does. But now the problem is that we have Lstar, or we have this kind of exact learning, but the teacher itself is abstract. Because the teacher does not know. The question is, how do we answer equivalence queries, basically? Because answering an equivalence query requires knowing what is inside the RNN. Right? So the intuition of what happens, and in reality it's more complicated, but at least the intuition is that we maintain basically 3 players now. We maintain the learner, which is here. We maintain the original network, the RNN, and a partition of the network somehow that induces a DFA. All right, and now we start asking questions. So any disagreement, so we check the partition, we check equivalence queries by comparing to the DFA induced by partition. And whenever there are disagreements, we check them using the RNN for ground truth. So the thing here is that the RNN, we can always use it as an oracle to ask membership queries that are answered precisely. So no matter what we did in our abstraction, we can be as wrong as we may be, or over approximate as we may be. Membership queries can always be answered by the RNN precisely. And the whole thing is based on that. So whenever there's a disagreement between the learner and the DFA, we basically, so this is a disagreement. Let's say they disagree on the word ABA, whether it is in the language or not. We go to the actual RNN, the concrete RNN, we run it, and it provides the actual response, which is, let's say, the word is in the language. And now, if the word is in the language and the DFA was right, then we refine the model held by the learner, right? Because the learner was wrong here. If the teacher was wrong due to abstraction, we basically refine the abstraction held by the teacher. All right, so it's kind of a game in which the teacher may also be wrong and basically improve its knowledge of what the network actually does. So that's the intuition. There's much more, it's more involved than that, and you can basically look at that in the paper. It has very cool applications. You can basically get concise, exact models from noisy data. So up to this work, there was no way to learn an automata from noisy data. Right? Because if you have noisy data and you run it on Lstar, it will learn all the noisy data as well. And this allows you to learn automata with noise. You can basically use it to generate adversarial example, knowledge extractor, etc. How much time do I have? Minus a few minutes. So I just want to. Okay, so I'll skip the examples. You can look at them in the paper. I just want to touch on one last thing, which is what can RNNs actually learn? And if you look at the literature from 93 or something, it says, listen, RNNs are Turing complete, right? Which is what we all know. But in reality, the proof requires like infinite precision floating point. The construction requires all sorts of complex things. And it turns out that in practice, this may be valid theoretically, but in practice, things are more subtle than that. And this is the most beautiful picture I've seen in the last year. I see a lot of pictures. I want to explain roughly what is going on here. So this is a depiction of the activations of LSTMs and GRUs trained to identify particular languages. So in this case, the language that we trained for is ANBN, and this is an LSTM. And what you see here, each line is a different dimension of the LSTM. And the point that I want you to get from this is that you see this purple guy here. It goes up to 1,000, and basically then starts going down. So what you can see here, intuitively at least, at the hand-waving level, is that the LSTM learned how to count. Right? The LSTM has an explicit counting dimension in which to identify A to the 1,000, B to the 1,000. It first counted the A's, and then counted the matching B's until reaching 0. Further, if you train it on A and B and CN, right, you can see that the yellow here counts basically the A's and then the B's, and whatever color that is counts the B's and then the C's. All right, so again, it kind of learned how to count. And if you look at the GRU at the bottom, you see scribbles like my son brings from kindergarten. And this is not a proof that the GRU cannot count, but the paper does have a proof that the GRUs cannot count, or at least not in this fashion, right? And I encourage you to look at that. Let's see the faces, LSTM equations. Yeah, you don't seem super excited. I'll try. Yeah? Are you super excited? Yes, okay, it's great. So I want to give some intuition to why the counting is possible or impossible by just looking at the equations here, just to give you the intuition. And so in the LSTM equation, if you look at the state, how it is computed, you can see that it is computed based on the previous state and the activation of the current state. And basically by controlling the input gate and the forget gate and the input gate, you basically can turn both of them to 1. And you can make this anything between -1 and 1. So what you have is you can actually encode the arithmetic operation of taking the current state and either subtracting or adding exactly 1 to it. All right? Because this is the result of tanh here, -1, 1. This is exactly 1, and so this is the previous state. You can take previous state and either do +1 or -1. Does that make sense? This is just arithmetic of equation. You don't even need to know that this is an LSTM, right? Just have to look at the math. This is -1 to 1. These could be 1s because they're the result of sigmoid, and so this is the way. And if you look at the GRUs, what happens in the equation, just again intuitively, you see that it interpolates the current state and the next state, and because of that, you cannot really encode this notion of doing exactly +1 or -1. You have to mix it somehow with the current state, which over time kind of deteriorates numerically. So you cannot encode an explicit counting dimension in the GRU where you could in the LSTM. So that's kind of the hand-waving explanation, and in the paper you can find more details of why this behaves the way it does. Just as a final note, the actual class of languages that are identified by LSTMs and RNN is not exactly clear. Like it can identify this A and B and C, and it does not identify other things. So something strange is going on. I encourage all of you to look at it in the paper and help us understand. We actually just barely scratched the surface there. Paper has RNNs as simplified K-counter machines, stuff like that. Again, just look at it. So to summarize, I think I talked about all of these things, the code2vec, the extraction at some hand-waving level, and just mentioned what RNNs can learn. So I'm done.
We are working on the open source implementation of code2vec, and we hit a few issues with the implementation. So first of all, as you said, it's quadratic complexity on the number of leaves. And this means if we have a large function, we explode because of the number of nodes, so we have to prune it very aggressively, or at least to find which paths are important, which are not important, and exclude them. The paper mentions that we prune by width and also by length, but sometimes the number is still very big, so we have somehow to exclude them. The second issue which we had is as you train on extremely large amount of code, let's say billions of lines, the space of all possible paths is so big that it's impossible to one-hot encode. It just becomes too big. So we have a suggestion that we could basically repeat the same trick with attention and try to train embeddings on paths. So it will be attention inside attention, and we can propagate and try to optimize this.
I have a better suggestion that is actually implemented already, which is to encode the paths using an RNN themselves. So the paths are natural. The paths are natural to encode with an RNN, and that's what works for us.
Performance considerations that RNNs can be sometimes slow.
So yeah, but we have a working implementation of encoding the paths with RNNs, and so that solves these problems. There are other ways to solve it which are simpler, which are different abstractions of the paths, but I'm not sure that this is super interesting to the entire audience, so we should probably take it offline. But there are many abstractions of the path that you can do that drop it by orders of magnitude and still give you good precision. Yeah.
So finally, we have noticed that the way the metrics are evaluated in the paper is the data is randomly shuffled across all the projects. And it's okay, but it's interesting to see how the metrics are reduced if you shuffle by projects instead.
What is the intuition of shuffling by projects? Why is that?
If you evaluate on the same projects in validation and on trained data set, you have a possibility of information leak. So this is why it's interesting to see if you shuffle by projects and do not mix code of the single project between validation set and the training set.
All right. We can try that. I don't think it will change it significantly, but we can definitely try.
Okay, so maybe since we're late, we'll take these further questions during lunch.
All right. Thank you very much. Thank you.